The last example that we will do is a family of examples. It's an example for any ring, although we're going to specialize just to Z, and then I'll leave it any ring to you on your homework. It's the same as what happens with just Z. There's no difference. But it's the evaluation homomorphisms. Now, evaluation homomorphisms are incredibly important, just incredibly important. And so let's get into those. So suppose that we're considering polynomials over Z, and let's pick our favorite integer. My favorite integer today is 0. So I'm going to call this ev sub 0, and it's going to be a function from Z to Z. In fact, let's spice it up a bit. Let's not go from Z to Z. Let's go from Z to let's see. Actually, no. Let's go from Z to Z. You can go from Z adjoint X. From Z adjoint X to Z. You can go from Z adjoint X to anything that contains Z. I'm going to just go to Z, but you could go to like R or Q, and you'll investigate that a little bit in your homework for examples of homomorphisms that are not epimorphisms or monomorphisms. Okay, but here's the domain and codomain of the function that we're calling ev sub 0. What is the definition of ev sub 0? So what it has to do is it has to take in a polynomial and produce an integer. Well, I know how to do that. I can take my polynomial and we can plug in 0. So let's think a minute for what this function is actually doing. So if we have a polynomial, an integral polynomial, again, this is where it doesn't really matter that it's integral, but somehow it's psychologically comforting that it's integral. It looks like that, right? And so if we plug in 0 into it, what happens? Well, when we plug in 0, all of these terms go away, and we're left with just, whatever the constant term is, because all the x's have to disappear. So this function, another way of describing it, maybe with words, is this is the extract the constant term function. And what we're going to do is we're going to show, or we're going to go in and check to see what of the orphisms it is. So let's start by seeing if it's a homomorphism at all. So we'll start with plus. All right, so we want to take two polynomials. I'm going to call them P and Q. You can call them whatever you want. And we're going to take their sum and then evaluate after taking their sum. So I've written a P up there. Let's also write a Q. B0 plus, possibly after extending by 0, they have the same, maybe you might need to extend one of these by 0 so that they have the same n. And so this tells us then that P plus Q is A0 plus B0 plus AN plus BN, x to the n. Now, some of the B's or the A's might be 0. That's okay. In particular, on the left-hand side, since we have to extract the constant term, the constant term of P plus Q is A0 plus B0. And ev naught of P of x is the constant term for P, so that's A0. And F0 of Q is the constant term for Q, and that's B0. All right, so is it compatible? I missed my orange. Oh no. Is it compatible with addition? Yes, it is. How do we know that? Well, look, it is. Let's see. The next thing we have to check is if it's compatible with multiplication. Now, I'm going to skip a step here. I'm not going to write out P times Q because we know what the constant term of P times Q is. It's the constant term of P times the constant term of Q. So this left-hand side, before I even write out my question mark, is A0 times B0. That's just how it works. And if you need to multiply them, sit there and multiply them. All right. On the right-hand side, we have the constant term of P times, again, the constant term of Q. Do we get the same thing? Yeah, of course we do. And then lastly, we have to check that it's compatible with 1. So the polynomial 1, I'm going to write as 1, which has 1 as the constant coefficient, and zeros for all the other coefficients. So what do we get? We get 1. Is that the multiplicative identity for the integers? Yeah. All right, we're golden here too. Great. So what can we conclude from this? We can conclude that phi is a homomorphism. Fantastic. Now let's ask the following question. Is phi a monomorphism? Now we have some intuition here. What is happening is we have kind of a lot of z's. We have a z for each degree, right? Because we can have any integer for the constant term, any integer for the linear term, any integer for the quadratic term, and so on. The terms have to eventually be 0, but we have a lot of z's here. And on the right-hand side, we only have one z. Now, it is possible to map z adjoint x to z in a bijective way, so that is 1-to-1 and onto. But it's not possible to do that in a way that is compatible with addition and multiplication. This extra structure that we have imposed on our mappings is actually going to tell us that it's not possible for these sets to have for this function to be bijective. So if you were to write down a bijection, if you know your set theory, if you were to write down a bijection, it's not going to be nice algebraically. So what that intuition is telling us, since we have this extra compatibility, is likely this guy is not 1-to-1. Likely this guy is infinite to 1. And in fact, that's true. So is it a monomorphism? Nope. And the reason is because all phi does is well, besides what I just said, all phi does is it extracts the constant term. So, for example, phi of 1 is the same as phi of 1 plus x is the same as phi of 1 plus x to any power is the same of phi of any polynomial with 1 as a constant term. In fact, let me just write out a random polynomial with 1 as the constant term. So is it 1-to-1? Well, none of these inputs are in general going to be equal to each other. So not only is phi not 1-to-1, it's like really not 1-to-1. So this tells us that phi is not a monomorphism. And if we're not a monomorphism, this would tell us that we cannot possibly be an isomorphism. And in particular, we cannot be an automorphism. In this case, we can't be an automorphism because the domain and codomain are different. However, there's another word here, namely, is phi an epimorphism? So is it the case that phi is onto? Well, yes. Take your favorite integer. Then take any polynomial with a as the constant term. Say p of x is a, the constant polynomial. Then phi of p of x is a. So is it onto? Right, because the constant term is a. Phi is the pick off the constant term. So is it surjective? Yeah, it is. So this is telling us then that phi is an epimorphism. Let me write it. I know I've said yes, but let me write it out. There's something to be said about writing sentences out using new vocabulary. Is an epimorphism. Okay, so this is an example of a homomorphism, which is not a monomorphism, but is an epimorphism. And you'll play with these evaluation type maps in class, And there's not a lot going on here, right? You know how to plug numbers into functions. So these evaluation homomorphisms are just plug something in. You know how to do that. In fact, we didn't even have to write P and Q out. You know that if you want to plug 0 into P plus Q, you plug 0 into P and you plug 0 into Q. It's exactly this guy here. And if you want to plug 0 in, the definition of plugging 0 into a product is you plug it into each one of the terms and then you multiply the output. So this is just, is this is it compatible with addition and multiplication? Well, it's just how you evaluate a function. So yeah, of course it is. And is it going to be the case that if you evaluate a constant function, the constant function 1, you get 1? Yeah. And in fact, absolutely nothing here is special about 0. So let me note that to end the video. In general, and which is something you're going to show, evaluation, so for any ring, R and element A and R, evaluation at A from R adjoin X to R, given by, take P of X, plug in A. This is always an epimorphism. So it's a surjective or onto homomorphism. It is always not a monomorphism, and therefore it is always not an isomorphism. And you'll prove that. And the proof is exactly the same. You replace all the zeros with an A, you replace all the Z's with an R, and it basically writes itself.